NASA's Perseverance rover saw something impossible: a single point of light on a world that should be completely dark. Think about that for a moment. For 4.5 billion years, Mars has been a silent planet of rock and rust. Its only light comes from a distant sun or its two tiny captured moons, Phobos and Deimos. So, what was this? The image arrived at the Jet Propulsion Laboratory in California. It was just another byte stream in a torrent of data sent across 200 million kilometers of empty space. But one analyst, working late, saw it. A glint, a perfectly focused reflection, sharp against the blurred Martian hills. The official logs state it was an anomaly. But the term anomaly doesn't capture the feeling in that control room. The silence, the sudden, a focused attention of a dozen scientists staring at a single screen. Your first thought is a malfunction, a dead pixel on the Mastcam Z camera, a sensor flare, or maybe a cosmic ray, a high-energy particle from deep space striking the detector at just the wrong moment. They run the diagnostics. The camera is perfect. They check the cosmic ray shields. Fully operational. This was not an error. The light was real. It was out there in the dust of the Jezero crater. And here's where it gets interesting. The light wasn't random. It appeared to be located on the side of a distant ridge about 2 kilometers away from the rover. It was steady, unwavering. It behaved exactly like a focused reflection from a smooth, manufactured surface. A surface that has no business existing on Mars. The questions started flying. Could it be a peculiar ice deposit catching the sun? Unlikely in that location and at that temperature. A naturally occurring metallic vein? Possible, but the reflection was too perfect, too concentrated. The official reports stop there. They mention possibilities, but they don't discuss the one possibility that every single person in that room was thinking. The one you are thinking right now. What if it was artificial? The team had a decision to make. Stick to the mission plan, analyzing rocks for signs of ancient microbial life, or turn the billion-dollar rover and investigate the light. They chose the light. The command was sent, a journey that would take days across treacherous terrain. Every meter forward was a risk, all for a single point of light. And as Perseverance rolled closer, the source became clearer. It was not natural. It was not alien. It was something far stranger. Is a mirror. The light wasn't from an alien city. It wasn't a natural phenomenon. It was the sun glinting off the thermal blanket of Perseverance's own back shell. The very shell that protected it during its fiery descent through the thin Martian air. You traveled across the solar system to explore a new world. And the first thing you discover is your own garbage. The back shell and its 21-meter-wide parachute were jettisoned on February 18, 2021, during the final moments of landing. They impacted the Martian surface at an estimated 126 kilometers per hour, just 2 kilometers away from the rover's final touchdown spot. A planned, controlled crash. But look at the images. Shredded metal, torn fabric, a debris field scattered by the wind. It looks violent. It's an artifact of our arrival. And this isn't the first time, not by a long shot. NASA currently estimates there are over 7,119 kilograms of human-made debris on Mars. Think about that number, 7 tons of junk. It's a ghost fleet of failed, crashed, and retired missions. You have the Soviet Union's Mars 2 lander, which crashed in 1971, becoming the first piece of human technology on the planet. The Beagle 2 from the United Kingdom lost on Christmas Day 2003, only to be found by an orbiter 12 years later, its solar panels only partially deployed. A silent monument to near success. Then there are the legends. The Opportunity rover, designed for 90 days, which ran for 15 years before a global dust storm finally silenced it in 2018. Its final message was essentially, "My battery is low and it's getting dark." We left it there, waiting. The official term is defunct hardware. A clean, sterile phrase, but what it really is a junkyard. And nobody is talking about the real danger it represents. The primary mission of Perseverance is to search for signs of ancient life. To do this, it collects rock cores, seals them in ultra-clean tubes, and leaves them for a future mission to pick up. The entire process depends on one thing: avoiding contamination. And here's the problem. What if a piece of that shredded parachute, which spent months tucked inside the rover's housing, gets blown by the wind and lands near a sample site? What if it carries a single, hardy bacteria from the clean room at the Jet Propulsion Laboratory in California? This is called forward contamination. The risk is so serious it's governed by international law. The Outer Space Treaty of 1967 requires signatory nations to avoid the harmful contamination of celestial bodies. Every component of the rover was baked at 110 degrees Celsius. It was scrubbed with alcohol, blasted with high-intensity light. But is anything ever truly 100% sterile? A single surviving spore, protected from radiation in the fold of a metal sheet, could change everything. The official reports downplay this risk. They have to. And this leads to an even more profound possibility, one that brings us to the title of this act: Havens in a Hostile World. Mars is hostile. The surface is bombarded with ultraviolet radiation. The atmosphere is thin. The temperatures plummet to minus 125 degrees Celsius. But what if our own debris provides shelter? Imagine a small crack in a piece of discarded metal. Inside, it's shielded from the worst of the radiation. Moisture from the thin atmosphere could condense there, creating a temporary, microscopic wet spot. It's a tiny accidental habitat, a haven. In 2020, Japanese scientists discovered the bacteria Deinococcus radiodurans could survive for 3 years in the harsh vacuum and radiation on the outside of the International Space Station. It's one of the hardiest life forms we know, and it's commonly found in soil and in clean rooms. The evidence suggests that some terrestrial life could, in theory, survive the trip, survive the landing, and find a foothold in the wreckage we leave behind. The wreckage we are now starting to find scattered across the planet. This changes the entire nature of the search. Suddenly, every glint on the horizon isn't just a potential discovery. It's a potential contamination site, a false positive, a mirror reflecting our own biology back at us. It forces us to ask the most fundamental and perhaps terrifying question of the entire mission. If we do find signs of life on Mars, how will we know for sure that it's Martian? The answer seems simple. You build better tools. You design a more precise trap, and you send it across 200 million kilometers of vacuum to get the truth. The problem is, our tools are not what you think they are. Meet Sherlock. It's an instrument on the end of Perseverance's robotic arm. Its full name is Scanning Habitable Environments with Raman and Luminescence for Organics and Chemicals. Think of it as a high-tech blacklight with a laser. It shines a focused beam of ultraviolet light onto a rock surface and looks for the telltale glow of organic molecules. These are the carbon-based blocks of life as we know it. When Sherlock's laser hits them, they fluoresce. They light up. A ghost in the machine. And here's the part nobody mentions in the press releases. Finding an organic molecule on Mars is not the same as finding life. Not even close. Many organic compounds can be created by simple geology. Water interacting with rock. Or they can be delivered by carbon-rich asteroids that have bombarded Mars for billions of years. So Sherlock can point to a spot and say, "Here are some blocks." But it can never say, "Something was alive here." It's a chemical detective, not a life detector. This is where its partner comes in. An instrument called Watson. It's a camera, a powerful one. It can take images so close you could see a single grain of salt. After Sherlock finds a promising spot, Watson moves in to take a picture. It's looking for biosignatures, the textures and microscopic patterns that life might leave behind. Think of them as tiny mineralized fossils. But this is where the science becomes an art. On Earth, geologists have argued for decades over whether 3.5 billion-year-old structures in Australian rock are the world's oldest fossils or just weird-looking crystals. They can hold the rock in their hands, they can slice it open, and they still can't agree. Now, imagine you're trying to do the same thing from another planet, using a robot, looking at a dusty image on a screen. You see a strange swirl in the rock. Is it the remains of a microbial mat, or just the way the sediment settled? You're guessing. An educated guess, yes, but a guess nonetheless. So, you have one tool that finds chemicals that aren't necessarily life, and another that sees patterns that aren't necessarily fossils. The official reports never frame it this way, but you have to ask, what are we really hunting for, and how would we even recognize it? This leads to the real mission, the one that underpins everything Perseverance does. The rover is not the lab. It's a collector, a cosmic courier. Its main job is to drill rock cores, each one about the size of a piece of chalk. It seals them in 43 hypersterile titanium tubes. Then, it drops them on the ground and drives away. The plan is to leave them there for another mission to collect, a mission called the Mars Sample Return. And this is where the entire grand strategy starts to fall apart. The Mars Sample Return is one of the most ambitious missions ever conceived. It requires a lander to touch down near the sample tubes, a small fetch rover to go pick them up, a rocket, the Mars Ascent Vehicle, to launch those samples into orbit. The first rocket launch from another planet, ever. Then, an orbiter built by the European Space Agency must find, capture, and seal that basketball-sized container in orbit and fly it all the way back to Earth. In 2023, an independent review board delivered a verdict on this plan. The budget had exploded from a planned $4 billion to a potential $11 billion. They concluded the schedule was unrealistic. The entire project is now in question. The official reason is engineering complexity. But there's another reason, a deeper fear. We call it back contamination. We've spent so much time worrying about infecting Mars with our bacteria. What if Martian life infects Earth? The samples, by international law, must be treated as a potential biohazard. They require a Biosafety Level 4 containment facility. This is the highest level of security on the planet, reserved for pathogens with no known cure, like the Ebola virus. Here's the catch. A BSL-4 lab designed for handling extraterrestrial materials doesn't exist. We are actively planning to bring something back from another world with no safe place to open the box. The irony is staggering. We send our best tools to hunt for life, but the tools are imperfect. We collect samples for a return mission that might never fly because it's too expensive and too dangerous. So after all this, the billion-dollar rover, the lasers, the titanium tubes, what if the best evidence for life on Mars comes from our own trash? Remember that Japanese experiment? They proved the bacteria Deinococcus radiodurans can survive for years exposed to the vacuum and radiation of space. Now, imagine we return to that backshell crash site in 20 years. And in the sheltered crevice of that torn metal, warmed slightly by the sun, we find a thriving colony. We will have finally found life on Mars. But it will be our own. We will have become the aliens we were searching for all along. Becoming the alien you were searching for is not a sterile scientific problem. It's a crisis of purpose. For the men and women at the Jet Propulsion Laboratory, this isn't just a job. It's a lifelong quest. Imagine you are one of them. You arrive at work before dawn. The room is dark, lit only by the glow of massive screens showing a world that is not your own. This is the control center for the Perseverance rover. Your coffee is cold. You've been at this for hours. Your job title is Rover Driver. You are one of a handful of humans who can say they have driven on another planet. You might be inspired by engineers like Vandy Verma, who has been driving rovers on Mars since 2008. You don't use a joystick. You write lines of code, thousands of them. Each command is planned with agonizing precision. I checked and double-checked by a dozen other experts, because a single typo could send a $2 billion machine tumbling into a ravine 200 million kilometers away. There's a 20-minute time delay for any signal to reach Mars, so you can't drive in real time. You're always living in the past. You send the commands for the day, then you wait, and you hope. The press conferences show the triumphs. They don't show the gnawing anxiety of that wait, the feeling in your gut when the telemetry is late. And what are you driving towards? The reason you do all this? It's not the debris. It's the ghost of a watery past. The team didn't choose Jezero Crater by accident. Billions of years ago, it was a lake, a deep, calm body of water fed by a winding river delta. Satellite imagery showed the clear outlines of that delta, a fan-shaped deposit of sediment exactly like the Mississippi River Delta on Earth. Think about what that means. Where there is water, there is the possibility of life. This is the real hunt, not for glinting lights, but for microscopic traces left in the mud of an ancient lake bed. And they found it. On Sol 190, the rover drilled into a rock. The data came back. It was volcanic rock, but laced with salt minerals, specifically perchlorates. On Earth, these salts form when a rock sits in water for a very long time. The water evaporates, leaving the salt behind. It was the smoking gun, proof that water was not just a brief visitor here. It was a resident. In the control room, there was no wild cheering, just a quiet, collective breath of awe. After decades of planning, after months of travel through the void, they had touched the shore of an ancient Martian sea. And this is the part nobody tells you. This moment of sublime discovery is constantly threatened by the mess you made getting there. Every plan must now account for your own junk. Wind models are run to predict where parachute fibers might blow. Drive paths are rerouted to avoid the debris field. The search for pristine, uncontaminated samples becomes harder. It's like trying to find a perfectly preserved fossil in the middle of a landfill you created. The irony is crushing. This changes the people involved. It introduces a note of doubt into their life's work. The mission is to find out if we are alone in the universe, a question that has haunted humanity since we first looked up at the stars. You have dedicated your entire career to answering it. You've sacrificed nights, on weekends, time with your family, all for one single, clear answer. So what happens if you finally find it? A microscopic wiggle in a drop of water, sheltered from radiation inside the wreckage of your own back shell. You found life on Mars, but it has your DNA. What do you feel in that moment? Triumph? Or the loneliest despair in the universe? Or the loneliest despair in the universe? What do you feel? The truth is, you feel both. Because this problem is no longer about a single rover or a piece of a parachute. It's about us, about our very nature. For decades, the goal has been clear. First robots, then people. NASA's Artemis program is the official roadmap, a plan to establish a sustained human presence on the moon, a training ground for the first human footsteps on Mars. Think about that. A person breathing inside a helmet, looking out at the red desert. A new home. The official documents detail every phase: the rockets, the habitats, the life support systems. But here's the part they don't publish in the glossy brochures. The 7,119 kilograms of debris we've left on Mars so far is nothing. It's the product of robotic scouts. The first human mission, a temporary outpost, would generate an estimated 100,000 kilograms of waste. A permanent base? The numbers become astronomical. We're not just exploring a world, we are preparing to bury it in our own artifacts. The Outer Space Treaty of 1967 was written for a different era. An era of careful, sterile, robotic ambassadors. It has no answer for a human sneezing inside a Martian habitat. No protocol for the billions of microbes in the human gut finding their way into the alien soil. So you have to ask a different question. The search may no longer be for life that was there. It may be for life that could be there. You see, perhaps we have been looking at it all wrong. We search for radio signals from distant stars, listening for an answer to the Fermi paradox, the great silence in a universe that should be teeming with life. We listen for aliens, but maybe life doesn't travel on radio waves. Maybe it travels on the soles of boots, in the folds of discarded metal. Perhaps life spreads not by grand design, but by accident, a contamination event on a planetary scale. We could spend a century searching for Martian life and find nothing, only to return 200 years later to find the planet teeming with the descendants of Earth's hardiest bacteria, thriving in the habitats we abandoned. We will have finally brought life to Mars. We will have become the gods we were looking for. And in that moment, when you stand on a terraformed world of our own making,